So everyone, please, we're about to start. We already have a bit of a delay, but that's okay. So welcome to the STARS seminar. Okay, STARS is an Stigam Sud and Fondesit Regular collaboration project involving students and researchers from the Universidad de Chile, the Laboratory for Analysis and Architecture of Systems of the French National Center for Research, the last NCSR, and the Universidad de Córdoba in Argentina. Today, we'll have 3 talks and 4 speakers. Our speakers are experts in satellite communication, Internet of Things, and nanosatellite development. Today, we'll have the talks back to back, and we'll have the questions at the end. So please, if you have any question, I ask you that you write them down so you don't forget about them. After the questions, we want to invite you to have coffee with us. This will be right outside this building in the campus courtyard. So now, please, let me introduce you, our first speaker, Juan Freire. He's a researcher. He's a researcher at INRIA in France, and he's an associate professor at the Universidad Nacional de Córdoba and the Saarland University in Germany. Today, he will be presenting his talk, Space Terrestrial Integrated Internet of Things, Challenges and Opportunities. So.
All right, thank you. Thank you, Ivana. Let me try if this works well. I think I'm touching other things. Otherwise, I can use.
Maybe.
You need to touch maybe. Okay, there. Okay. Yeah. Okay. Well, thank you for the introduction, Ivana. So my name is Juan Freire, and today I'm going to present you some thoughts and ideas and concepts around space terrestrial IoT, which is one of the core topics that we have at the STARS Stigam Sud project nowadays. And I want to touch some topics about what's the idea of satellite IoT, what is the architecture that we are thinking possible to in order to materialize satellite IoT. And then I'm going to discuss some challenges that emerge from thinking, especially a LoRaWAN based IoT technology for connecting satellite IoT systems. So what I'm going to tell you today is basically, I'm going to be quite short. I only have 30 minutes because I will then hand over to Pascal and Laurent, who are in France, and they are going to deepen in some synchronization topics. But I'm going to touch today some general concepts, which has been recently published into an IEEE Communications Magazine article, which is this one that you see on the screen. And you will find there some further details and more in detail discussion of what I'm going to present today. So first of all, some general motivation. So satellite IoT is quite interesting, mostly because there is a very little percentage of the surface of the planet which is actually covered by mobile communication systems, like as we know it. And this, of course, includes Internet of Things networks. And there are plenty of applications with rest outside of this surface of coverage. And of course, we're also thinking about oceans and deserts and forests and mountains and regions we don't have any type of coverage, but still have some economical value or projects that needs to track and monitor elements which are outside of coverage of the mobile network infrastructure that provides services nowadays in the urban environment and in rural environments in many cases. But we do also want to monitor and collect data and probably send data to devices which are located outside of this coverage. So this is where space terrestrial integrated IoT comes into place. And we say space terrestrial integrated because we don't want to have a specific IoT services for these remote regions and a different IoT services for regions which are under coverage of the urban and the classical IoT systems like that we have nowadays, which are thriving, especially in the context of low power wide area networks such as LoRaWAN and such as NB-IoT. So we want to have an integrated system that provides services to both paradigms, to say somehow, and this is why we say this is a space terrestrial integrated IoT, because we want to have a satellite that can communicate to a device that can also communicate with the terrestrial ground infrastructure. We're talking about uplink and downlink, so this is what we mentioned with directional communications. We're talking about dense and sparse constellations because we are thinking of satellite constellations which can have hundreds of satellites that are continuously covering every point of the planet. So similar to what we are seeing nowadays on the media with Starlink or this type of mega constellations that are becoming more and more popular. But also we want to think of systems that maybe can operate with just a few satellites, which has kind of an opportunistic connectivity with the different regions of the planet. So namely, there is a low Earth orbit satellite that pass over and have maybe a 10-minute window with a connectivity with a device over there, but then that device can remain offline for several minutes, if not hours, until a next satellite appears in the horizon to establish a connectivity. So we try to consider these both type of systems. And of course, we want to keep the low cost property. And this is basically achieved by having the same devices or very similar devices to those that we have on the classical IoT systems as well. So since I'm giving the first talk, I think there is some basic concept that we need to convey before continuing talking about satellite IoT, which are the type of orbits that we typically think and observe in this type of systems. So on the left-hand side, we have the classical geostationary orbits, which is an orbit that rests at 35,000 kilometers altitude. And the satellite in a geostationary orbit is typically laid down on the equator plane, and the satellite is seen as a fixed point on the sky if we are standing on ground like us. So namely, the satellite is kind of a fixed star on the sky, and this has traditionally brought quite a lot of advantage to establish a communication link with such a device, because you can just point a high gain antenna to that satellite, and that will remain fixed on the ground, and the link can be established in that way. But low Earth orbit satellites, or LEO, on the right-hand side of the slide over here, orbits at much lower altitude, which is of course much more beneficial for IoT devices because the range of the channel is much lower. We're talking about around 1,000 kilometers altitude, but we also have satellites orbiting at around 300 kilometers, which actually makes IoT links much more possible. But the issue of LEO satellite is that they have a very high orbital speed of around 7 kilometers per second. So this basically makes that satellite that appears in the horizon and disappears in the other horizon in between 5 to 10 minutes, depending on the angle of approach of the satellite to the given point. So this brings the problem that we have. Although we have a lower, shorter range channel, which is better from the link budget perspective, we have the problem that this is highly dynamic channel, in the sense that in the horizon you can have a few 1,000 kilometers, then on top of your head you can have a few 100 kilometers, and then that satellite goes away, increasing again the satellite range and so on. But still, for satellite IoT, we are quite interested in LEO satellites because of the reduced distance to the IoT device. Although there are some satellite IoT applications that also use geosatellites in some specific cases. But the main question, and trying to break a little bit the skepticisms about this, is that, well, but can an IoT device, which is so small and so scarce in terms of energy resources, able to send a signal to a satellite which is 100 kilometers distance from the device position? And this is a physical layer question on the first hand. We're just talking about sending some radio frequency signal, and that some device so far away is able to pick it up. And in fact, the answer to the question is yes. And these are some examples over here of very small devices with some references underneath that you can take a look at, that are already designed and has been tested to transmit signal to such a far away gateway, in this case orbiting in a satellite. So here we're talking about mostly about direct to satellite IoT. This is kind of a specific family of satellite IoT, where very, very small devices on ground can emit a signal in such a low data rate and of course a very low power, that still can be decoded in an orbiting satellite. In this case, we are talking about mostly about these very small satellites. We're talking about CubeSats. So Marcos Diaz is going to, of course, provide some inputs on this on a talk afterwards, which are because of the very low power of the signal, because of the very low power of the whole IoT setup that also exists, of course, in the urban environments, we are able to think on very small satellite platforms to actually implement the required gateways to collect the data and, of course, to transmit data back to the devices on the surface. On the top part of this slide, we can see that these Argos, AIS, and ADSB are also classical IoT-like protocols that exist in space for many, many years already. So these are low power, long range, but low data rate systems that operates with satellites already. But the problem is that they are not standards that are supported in terrestrial IoT systems, like we know nowadays. So the challenge is to move into this integrated approach where we leverage, for instance, LoRaWAN and NB-IoT, which are standards that are supported in the urban environments, so that we can move this technology and possibly learn from Argos and so on, and make the required modifications or adaptations in order to also use LoRaWAN and NB-IoT in the space environment, so that we can use the same IoT device to connect to a ground system or to connect to a space system. This would be the holy grail of satellite IoT, in our opinion. And this is also not only our opinion, but also the opinion of many, many companies that are listed underneath here, which are actually pursuing this task, because besides being an interesting topic, it's also quite a promising, let's say, economical advantage if we can actually achieve to do that, because we will be able to sell very cheap devices as what we're selling already for terrestrial IoT, but that also can serve satellite IoT. So these are not satellite-specific devices, and this, of course, can take advantage of the massive manufacturing of these IoT devices and so on. So also from an industrial perspective, this is highly appealing. So then, if we think then how is the architecture of this integrated IoT system, then we have like kind of three parts. So we have like the urban classical scenario with very high connectivity that exists as nowadays in IoT systems. So like, again, I'm touching again quite a lot on LoRaWAN and NB-IoT, which are the low power wide area IoT solutions for long range links. But then also we have kind of two satellite IoT families of this type of systems. So one of them is what we know as indirect to satellite IoT, which would be the one here in the center of the slide, where the device is not directly connected to the satellite, but is using kind of an intermediate gateway to do that. So namely, what I do is on the surface of the service region where I want to provide connectivity, I can locate a ground gateway which acts as a concentrator of the data, and then that gateway is the one in charge of connecting to the passing by satellite. Because of that we have a ground gateway, we are able to possibly think on a gateway which is a little bit more rich in resources and can possibly establish a link with a geostationary satellite, for instance, at the beginning. So you will see that geosatellites are more applicable to this type of satellite IoT systems where there is a concentrator on the ground that has possibly a high gain antenna and some energy that can actually have established a link with the geosatellites. But on the other hand, if we think on devices that want to directly connect to the satellite, on the left-hand side here of the slide, then we are talking mostly about LEO satellites because of the shorter distance to the devices. And therefore, here is where we're talking about direct-to-satellite IoT, where the device is able to directly communicate with the satellite. From a research perspective, we are mostly focused on direct-to-satellite IoT, which is quite more challenging because of the distance and the low power of the devices and the medium access control protocols that are required here. So we're mostly focusing on that part in the STARS project at the moment. But the challenges that emerges from this configuration are quite a lot. So we're talking about challenges on the radio access network. So namely, there will be a satellite that will be covering possibly hundreds of thousands or even millions of devices. So the access and to a shared radio medium, it becomes stressed quite a lot, farther beyond even than what we see on terrestrial IoT. Also, the core network becomes quite a challenge, and there requires some thinking. Now we don't have a stable core network like NB-IoT or LoRaWAN system in terrestrial environment, but we have a satellite and possibly satellite-to-satellite multi-hop link that can be severely delayed, that needs to be taken into account in all the core communication functions of the system. And then we have a bunch of software and hardware elements that will need to be required to be developed in order to this to become real. So we're talking about how do we handle synchronization with millions of the remote devices. We're talking about how can we locate those devices. We need to know where they are so that we know when the satellite passes by of that device, how to reach them. We're talking about what happens with mobility and routing in this context. So we're talking about multi-hop links in satellites. We're talking about also when to transmit, when to receive in order to optimize the energy of the device, but also of the satellite, because now the gateway, which is a satellite, is also resource constrained as well. So we need to take into account also the limitations of the satellite platform. We're talking about the core function virtualization and localization system, basically, because as we see on the right-hand side here, if we see the standard of LoRaWAN or NB-IoT, we're talking about a lot of functions that rest in the core part of the network that now might need to be moved, or at least some of them will need to be moved to the satellite part, because maybe the connection from the satellite to the core network ground might not be as stable or as basically might have high latency in connectivity. So some functions might need to be migrated to the satellite. This is an open question. This is something that is not yet answered. And of course, we're talking about how do we design, how do we operate, and how do we evaluate this type of systems. So quite a bunch of challenges around this. We have also recently an accepted ANR project in France with some French partners that are also, including last, Pascal, we will present next, that will hopefully give us some resources to observe and check on this problem and try to provide some required advances. Tomorrow, Friday, we'll have a workshop on one of the tools that we are developing to evaluate satellite IoT. This is called FloraSat. This is quite a new simulator that we are developing nowadays together with Diego and some folks at IRIA in Lyon. And this is hopefully a new tool that can help us to approach all of these problems that I mentioned before and try to evaluate and compare different solutions. It's quite a powerful tool so far. It's based on C++. It's an .NET++ based simulator tool that extend on some existing simulators around the community, because we had very good IoT simulators and we have very good satellite simulators, but we didn't have a simulator that actually integrates both domains. So FloraSat, in our understanding, is the first one that actually blends both domains and allows us to make some good evaluations on this type of systems. It includes, of course, orbital mechanics. We have inter-satellite links. We have different flavors of LoRaWAN for the moment. We don't have NB-IoT. This is kind of a future research topic that we want to tackle sometime. For the moment, LoRaWAN is much more simpler and help us to push forward the research in a more streamlined way. And yes, and we have different models and so on. So we're going to be talking about FloraSat. If you want to join tomorrow, we have a few hours to teach you how to install it, how to use it. And this is, of course, under development. So we will talk about the open challenges that we have with the simulator tomorrow in the workshop. So please register if you want, if you're interested, and we can provide further details on the tool tomorrow. What I want to do before, I don't want to take so much time from Pascal. I think I have around 10 minutes still. So I want to touch on three not so intuitive topics that emerges from first experiment that we were doing in FloraSat with satellite IoT, which are rather conceptual issues that quickly appear when we want to migrate, specifically LoRaWAN. As I mentioned, we're focusing on LoRaWAN for the moment. When we want to migrate LoRaWAN to the satellite domain. One of them is intuitive, which is the interference in the uplink direction. So uplink direction, we're talking about the thousands of devices on the surface that want to send a signal or transmit data to the passing by satellite. The issue on this case is that typically the cone of coverage of a satellite is of course quite big. That's the idea of a satellite. We want to cover a very big surface on the planet, and we are possibly talking about hundreds of square kilometers of surface. What happens in that case is that part of that surface can actually be already populated with devices from the same technology that you're using for the satellite IoT, or possibly other technologies that are generating interference on the channel that you want to use to uplink the data. So you can have internal interference and external interference. One way to deal with this issue is, of course, move to a regulated frequencies in such a way that you ensure that that bandwidth is only for you, and then you can control your devices somehow. And this is kind of the approach of MBIoT, which is a branch of 3GPP standards that are coming from 5G and so on. So these are typically thought for operators that already own a part of the spectrum and they can safely use it for transmission purposes. But in case you don't have this, then what you can do is, of course, try to split the coverage area of the satellite into multi-beams, which are basically focalized beams into different regions, and therefore you reduce the interference because you're not picking all the interference from the many regions. But the problem of that is that, of course, you typically need more complex antennas to do that, right? You need like typically multi-array antennas and so on. That, of course, makes the satellite more complex. So we're talking about that we also want to keep using efficient CubeSat platforms that might not have the chance of accommodating a huge antenna array or something like that. So also this is not a solution that we'd like a lot. A possible solution is to also use cognitive radio. So this type of cognitive radio system that try to sense the environment, understand where the interference is, and therefore try to use the piece of the spectrum that is not interfered. But the issue with this is that this on the one hand is kind of immature, and on the other hand, the devices on the surface will likely be unable to perform such a cognitive function because of the limited energy and the limited computation power that they have. So also this is not a really appealing solution. And this is a problem we have not discovered. This is a problem that also was already discovered by Semtech. Semtech is the company that actually invented LoRa on the first place. And they are, since a few months ago, they're pushing forward what we know is a new LoRa modulation for IT, which is called long range frequency hopping spectrum. So this is a very long acronym there. And the idea of this modulation is, as we see here on the slide, is that instead of sending this chirp spectrum that is used by LoRa in a given bandwidth, so in this case, this is bandwidth on the y-axis there, and therefore the LoRa packet would be the gray area over there that use a chirp spectrum over such a bandwidth. What they do is divide the bandwidth into very, very small subchannels. We're talking about subchannels on the order of 488 hertz, so really, really small bandwidth time channels. And then what the devices do is just split the transmission packet into very, very small pieces. And they basically use a frequency hopping technique so that different pieces of the packet are sent and replicated over different subchannels in a random way, basically. So what you achieve then is kind of have like this scatter of the packet into the time dimension, but also in the frequency dimension, in the expectation that destructive interference will appear into only some parts of this time frequency domain here. And therefore you will be able, because of the packet is also replicated in many places, you can pick up the required parts of the packet plus some coding solutions on top of that, so that you can recover the packet even on very high interference scenario. And long range frequency hopping spectrum can of course be used for terrestrial IoT, but the main motivation of Semtech by introducing this modulation is for the uplink of the satellite IoT solution that we are also discussing nowadays. And this is really, really new. There are only 2 papers around, like with solid contributions around this topic. There is the first one that was presented that actually introduced the overall topic to the community. It was all around a year ago. And then we have a new paper that actually studies a little bit more this modulation in the satellite domain. But this actually brings a lot of open opportunities that we have to discuss. So for instance, what happened to how can you optimize the hopping pattern, for instance, for the satellite case, or in different interference scenario, or how can we establish some efficient techniques to recover pieces of the packets that are lost, and then how we can reconstruct the packet in a very efficient way. So there are a bunch of opportunities there to do research around long range frequency hopping. Maybe the issue of long range frequency hopping is that there is not, for instance, the papers that present this modulation does not provide information on which is the modulation that is used on each of the subchannels, for instance. We don't know that yet. So there is also the option of doing some kind of reverse engineering, because this modulation is already provided into commercial chipsets from Semtech. So even the chipsets that are already being shipped for terrestrial IoT, they already include this modulation. And in principle, we should be able to study this from just using software-defined radio to decode the signal and try to understand what's happening there. Which is kind of what happened with the very early LoRa modulations that were also closed. These are physical layers which are controlled by Semtech, and you can do some kind of reverse engineering there and try to understand what's happening. So I think there is a lot of opportunities to do around this new modulation, especially in the satellite context. That's on the uplink direction. We're talking about device to the satellite, but then I think there are two more challenges also interesting to discuss from the satellite to the device perspective. And this is also around LoRaWAN. And according to the LoRaWAN specification, what happens is that when you execute an uplink, namely a transmission from the device perspective, after a given fixed time, you open what is a reception window afterwards. So this is the downlink opportunity where the device basically listens to the environment and is able to receive a downlink packet from the gateway, from the LoRaWAN gateway. This is fine, and this works perfectly fine, especially in terrestrial IoT, where the gateway is connected to a network server, which is connected via internet, basically. So the gateway that receives the uplink sends the packet to the network server, and the network server, exactly 1 second or something later, can send a downlink packet that will be delivered to the device, which has this reception window open here, ready to receive that message. This works well when we have internet. The Zoom reconnected? Okay. So I'll continue anyway. So as I mentioned before, internet has close to zero latency, and therefore the network server is immediately connected to the gateway. So namely, we have this connection with zero latency. But when we talk about satellite connection, the latency will not be zero for sure. We have multi-hop satellite links and so on. And therefore, the latency from the server back to the device can be quite significant. And you need to account for that in order to send the packet at the very right moment so that the packet arrives to the device during the reception window. Otherwise, the device on the surface will just close the reception and you will lose the downlink opportunity. And this requires some very accurate scheduling techniques on the server side so that you are able to compute and guess or learn which is the latency of the satellite network so that you are able to shoot the packet on the right moment. Otherwise, you can make more intelligent gateways that basically can store this downlink packet in advance and send that packet on the right moment to the device on route. We have the very different architectural options there to deal with, and this is what we're trying to look at the moment. Finally, I think this is one of my last points today. I'm right on time. So another issue that we have found with FLoraSat is that because of the orbital dynamics and the different configurations of the satellite, particularly in the North and South Pole, your orbits try to get like closer together because basically the polar orbits, satellite gets closer in the poles. And we have situations where we have multiple gateways that are covering the same area. And Santi will be giving one of these talks. Santiago is working on this topic, which is computing and understanding how these dynamics multi-satellite area actually evolves in time and so on. And the issue that happens here is that, again, devices on the downlink, as I mentioned before, they open this very strict reception window, and there is a gateway that will transmit that packet to such a reception window, which is okay when we have a single gateway. But when you start having multiple gateways that actually overlaps, then we have the issue that if these two devices over here has sent an uplink message quite at the same time, they will also open the reception window quite at the same time as well. And they will both have overlapping reception windows open. This occurs actually quite often, and this is what this plot over here tried to show, that as we grow to a few hundreds of devices, we see that this happens more and more often. And having two reception windows open at the same time at devices which are close by and are covered by multiple gateways at the same time, a single downlink message that was scheduled for this device will actually be picked up by this other one, even though the downlink message for that device was going to be transmitted by another satellite. So there is a confusion there on how can I multiplex actually, how can I divide the different downlink streams from different satellites, which are covering the same region at the same time. And these devices have basically no way to know which packet is for them before they decode the packet completely. So they will need to use all the reception window, get the preamble, decode the packet, open the packet and say, oh, I am not the ID of the packet, I will need to drop it. And this is something really negative because the device has already wasted all the energy into doing all that effort. And the satellite also wasted the radio resource on sending that packet. And this is also one of the issues that LoRaWAN seems to have that becomes quite challenging and problematic in the satellite IoT context. This is something we need to solve. The idea that actually can help us is to be very smart on a network server on which satellite we want to use to execute the downlink in such a way that, that the satellite that execute the downlink will only have one device with the reception window open and the coverage, and then the gateway on the other side we only have. So for instance, in this case, we might have wanted that satellite to execute the downlink for this device and that satellite to execute the downlink for this device so that they don't collide and they do not overlap on the reception receiving devices. So this is also another kind of structural problem that we see on LoRaWAN based satellite IoT that also requires some research and understanding on how to deal with. So so some takeaways of my talk today. So we introduced this space terrestrial integrated IoT idea and concept that is pushing forward some interesting research topics. We mentioned this is of course attractive from let's say from an industrial perspective, but also from a research perspective. And there is also feasibility behind this. I mean, the link can be established. Now the question goes maybe to a little bit higher layers, so namely the medium access control, the network layer, how do we operate the system, how do we deal with this issue I presented before. And we also introduced FloraSat as a new simulator tool that can help us to understand this problem and test and evaluate solutions for those. And then we touched some specific LoRaWAN issues that we are discovering with FloraSat at the moment in the uplink and the downlink directions. And of course, the perspective is of course to keep working on these topics. We want to have long-range frequency hopping implemented in FloraSat sometime soon. We're also working on testing different uplink and downlink transmission policies. We have students even in the context of the STARS workshop project working on network size estimation problems with satellite IoT, different channel models that we can also use and implement on the simulator as well. But also some core network features and questions which remains open. So how do we deal with the intersatellite linking routing, which is the optimal way of routing data between these very small CubeSats? And of course, this is a question that even goes beyond satellite IoT, it's a more general one. How do we synchronize with the devices? How do we deal with mobility, with roaming? What happens with devices that move from different regions to another? So there are plenty of research questions around satellite IoT, which in my opinion are really interesting to deal with, because many of these questions can actually, answers to this question can actually make an impact in other satellite systems as well, and not only IoT related. And the good, in my opinion, the good point of this is that satellite IoT is really thought for operating on reduces resources, and we can use cost-efficient CubeSats to test them. We are not talking about Starlink satellites, which have a 700 kilo wave and cost millions of dollars to test these type of things. We just need some small CubeSats and some small devices on ground to make this type of test, and we can do research with limited resources, which is what we have. That basically is the end of my talk. So yeah. So thank you for listening, and I will hand over to Pascal if he's connected up there.
Yes, I'm gonna check that now.
Yeah.
So thank you, Juan.
Yeah, thanks.
Okay. So I could stop sharing the stop sharing. And so now the participants that are here can see our next speakers. 1 second. There you go. So now I would like you to present our next speakers, which are Pascal Berthaud and Laurent Chasserat. Pascal is a researcher at the LAS NCSR in France, and is an associate professor at the Toulouse University of Science. Laurent is a PhD student at the LAS NCSR in France. And today they'll be presenting their talk, Why Synchronization is Needed in Low-Power Global Area Networks. Now, if you can please share your presentation. So if you have any troubles, yeah, there you go. Now, let's this. Okay.
And now you should hear me too. Is that okay?
Yes.
Okay, perfect. So
yeah, here, so we don't have any interference. Okay.
Okay, perfect. So good morning to everyone, even though it is the afternoon here in France. Today I have the pleasure of presenting with my PhD supervisor, Pascal Berthaud. And we are going to talk about why synchronization is needed in low-power global area networks. So in fact, we are going to split this presentation into 2 parts. In the first part, I will present my latest thesis work, which is about synchronizing LoRa networks on the ground. And then Pascal will talk about the specificities and the difficulties envisaged when bringing this work into satellite networks. So let's start by synchronizing LoRa networks on the ground. And with that, I will present LoRa Sync, so an energy-efficient synchronization mechanism, which is designed to provide a robust synchronization to LoRa devices, but also remain energy efficient, since this is a key requirement in LoRa networks. So first, I will give some background about my thesis and my previous research. Then I will describe the design of the mechanism. After that, we're going to have some part about performance modeling. And finally, I will quickly present a proof of concept of this mechanism implemented on real hardware. So first of all, a background about my thesis. I guess that you all know here the LoRaWAN architecture, but I'm going to remind it. So we're dealing with a set of end devices that communicate with gateways through LoRa communications. And then the gateways are in charge of forwarding messages to a centralized server on the internet. So typically, we say that this is a star of stars topology because a lot of devices are communicating with just a small number of gateways. And about my thesis problematic, we can already find it in the name of this kind of networks, since LoRaWAN are part of what we call low-power wide area networks. We quickly see that when trying to design a MAC protocol, it's going to be difficult to combine both throughput and energy efficiency. Indeed, in LP1, so we have the low power part, which implies devices that are energy constrained. And so that's why the legacy LoRaWAN access was based on pure ALOA, which does not require synchronization in order to save energy, to avoid that we have devices that have their radio turned on to listen to some kind of synchronization mechanism. However, since we also have the wide area part in LP1, we know that we are prone to have many colliding devices. And potentially, when the network traffic increases, we're going to face scalability issues with the asynchronous access. So in order to fulfill the throughput requirements when the traffic load increases, we have chosen to follow the path of synchronization. And so we will see in this presentation, and in fact, that's the topic of my whole thesis, that it's difficult to have both at the same time, and that depending on the situation, we're going to have to find trade-offs between throughput and energy efficiency. So, having said that, I'm going to present now a previous work in my thesis about a first step towards synchronizing LoRa networks. So we know that in the legacy protocol, we have the class B, which in fact is already a synchronization mechanism, but it was designed to increase the downlink performances. In fact, with class B, devices have to listen periodically to beacons. And thanks to this shared time reference, they have to open reception windows, allowing the server to send them a downlink message. Whereas if you stay in class A, the server has to wait for an uplink communication first before sending a downlink message. So the idea behind the class S that we presented in a previous contribution was that we could reuse the same beacon-based synchronization, but use this time reference to design uplink transmission time slots that are tailored to fit the longest frame time on air allowed in the network. And this way, we can already switch from a pure LoRa access to slotted LoRa, which doubles the network capacity. So it's a first step towards increasing the performances of LoRa networks. However, that was theoretical work, and recently we have been implementing this onto real hardware. So to do that, we had to take into account new constraints that are real hardware constraints. And doing that, well, first, let me present the testbed that we have implemented. So for the devices, we have PyCom low-pi 4 devices from PyCon. We use Raspberry Pi 3 gateway combined with an EMST concentrator. And one thing is important here is that in order to be able to trigger synchronization beacons, we needed to be able to trigger downlink transmissions based on timestamps. And to do so, even on the ground, we had to add a GPS chip to our gateways in order to have a precise synchronization and to have a clock signal directly linked to the concentrator, allowing to trigger the transmissions with a great precision. And we completed this testbed by a custom server linked to MQTT broker, which is in fact the one used in the ChirpStack architecture. And so first of all, we used this testbed in order to understand really well what were the constraints we had with this hardware. So the first thing we did was measuring and modeling the clock drift. So generally, the clock drift in this kind of experiments is modeled by the simple skew model, SKM, which considers that when the temperature is constant, the clock drift is simply follows a linear model. So when we measured clock drift on real devices of our testbed, we see that it was kind of true. It's the clock drift seems to be following a linear trend. However, there is also additional noise, for which we haven't clearly identified the cause, but it can be many things. In fact, all our devices were connected to the same alimentation power supply, and also in the same room. So it might be because of temperature variations or some perturbations in the hardware that made that we had noise. And we decided to model it as well because we want our synchronization to be robust. And so we don't want to be bothered by some kind of noise which could create transmission misalignments. So we use this kind of model, which is inspired from the drift model, but has this additional noise margin. That said, we are ready to design our synchronization mechanism. We have two objectives that follow the main objectives of my thesis. So we want our synchronization to be robust. So we want to be sure that our devices transmit their messages on the time slots without overlaps. But we also want this synchronization to be energy efficient. So for the robust part, we have taken the work I already presented for class S, And we have added additional transmission margins at the extremities of the slots to make sure that the transmissions will have these margins tailored on the worst case device drift that may occur between synchronization events. And so once that is said, in order to make the synchronization energy efficient, we also implement a beacon skipping mechanism, because it was shown in the past also that the beacon receptions are a great part of the power consumption, and that skipping some of them could allow to reduce this power consumption a lot while keeping satisfying synchronization. So these are the two great ideas of the mechanism. First of all, the margins that are based on the worst case drift, and the beacon skipping mechanism that allows us to save power by synchronizing only when it's truly needed. So now I'm going to talk a little bit about the performances of protocols running on top of this synchronization mechanism. Since we are still studying throughput and energy efficiency, we're going to study these two models. So let's start by the throughput modeling. So we model both the legacy access, so class A, which is based on pure ALOA, and a slotted ALOA access, so very simple ALOA method, but that profits from the TDMA induced by our synchronization mechanism. So we use the most standard modeling with a finite number of devices. So we use a Poisson process to model the arrival, the generation of frames. So we have P, the probability that a frame is generated during a frame time. And we know the pure ALOA throughput expressed as function of P. So it's the black curve here, and we can see that our model, so this equation, fits the simulations that we have made on a large scale, on a simulator that mimics a large scale environment. For the modeling of slotted ALOA over class S, we have to adapt its probability to the probability that a packet is generated during a LoRa sync slot, because we have not only the packet time, but the addition of the two margins. And, and we also have to consider this coefficient, which in fact represents the time available for transmission over the overall time. So it's the number of slots available per beacon period. And similarly to the slotted ALOA throughput, with the small tweaks we have, we get these throughput equations, which also depends on the margin value, so delta max. And we plot the throughput for the model and the simulations, check that the results are validated, and we see that the bigger the margins are, the smaller the throughput will be, which makes sense because a greater part of the bandwidth is available for transmissions because the margins are smaller. Now, let's go on to the energy efficiency modeling. So to model energy efficiency, we in fact have to model first the power consumption. And then the energy efficiency is obtained by dividing the throughput in bytes per second by the energy consumption, so in joules per second. So we have the bytes per joule, which is a typical unit of measure of the energy efficiency. So to do so, the power consumption, we consider the power consumption of each device in the different states, so transmission, reception, and sleep. And we ponderate that by the average time spent transmitting, receiving, or sleeping. So to do so, we have to introduce the reception slot rate. So this is associated to the class A reception slots, and the beacon reception rate for the reception of synchronization messages. And so once we do this, we divide the throughput by the power consumption, and we get this energy efficiency figure. So we can see that once again, the models are validated by the simulations we have made. But here we also see something that's more interesting. So in black, you have the pure ALOA curve. You see that it is associated with the maximum energy efficiency for the low generation rates. And then after a given threshold, we see that the slotted access becomes more energy efficient because we reduce the number of collisions and so the energy efficiency becomes better. But what's also interesting to notice here is that depending on the rate, the most efficient slot size and margin size varies as well. So we can see that when the slotted access becomes preferable here, it's the biggest margin size which is associated with best energy efficiency. And when the generated traffic increases, you see that it's smaller and smaller margin values that becomes preferable. So we pushed the study a little bit further and try to estimate and try to find a methodology to estimate the most energy efficient slot size for any given generated traffic. So we still keep a study based on the same generated traffic scale. And we varied the slot size with the model established previously. And we evaluate the energy efficiency of the pair between the traffic and the slot size. And for each slot size, we find the maximum, for each generated traffic, we find the slot size, which is associated with the maximum energy efficiency. And so that is what is plotted here with the black dashed line. And we can see that, as we saw just before, as the generated traffic increases, the slots should be made smaller and smaller, which makes sense because when the generated traffic is low, we don't have that many packets to transmit. And so it's acceptable to reduce the power consumption at the cost of an increased margin, and so worse use of the bandwidth. However, when we get more and more packets, the collision probability increases, and so we benefit from having more slots in our slot frame, even if we have to synchronize more often, and so spend a greater amount of energy in the reception of synchronization beacons. So that's it for the modeling part. Now I will just quickly show a proof of concept of this mechanism on the testbed. So of course, on the testbed, we had only a few devices, so we were not able to make studies on a large number of devices like before. But on a single device, we can see that we are already able to observe the clock correction. So in this figure here, you have the drift of one single device, and here are plotted in black the beacon reception timings. And every time we receive a beacon, we see that. So it's not really clear to notice here because, as I mentioned before, there is this noise around the linear trend of the drift. But if we plot the model around, we can see that the drift remains within the model and that the clock correction is being done correctly. So to conclude, I would like to maybe give a word about the methods used in this contribution. So personally, what I like about this work is that we started from observation on real hardware, so with the clock drift equations. Then we went onto the design phase. We modeled the protocol that we have designed with math, so the mathematical modeling. We validated this modeling with simulations, which allowed us to approach a large-scale scenario, which is not possible with the testbed. And finally, we went back to the testbed to assert that the result still works and to close the loop in a way. So we have the hardware, which is really slow, but really accurate. We have the simulation, which is a bit faster, but only as accurate as you make the simulation. And finally, the mathematical modeling, which is extremely fast, but where you have to make a lot of hypotheses. So by using these three tools complementarily, you have, in my opinion, something that's a bit more sure. And yeah, so that's it for this part of the presentation. I will now leave the floor to Pascal, who will explain what difficulties we could have taking this work that we have shown operates correctly on the ground and push it to the satellite networks. So thank you very much. And I will stop sharing the screen.
Thank you, Laurent. Pascal, can you share your screen?
Yes.
Okay, thank you.
Okay.
Yes, we can see you.
Okay, you have no more problem of hearing us?
No, actually, we managed to solve that
Okay,
after a couple of times, so we
okay,
heard
perfect.
the last part.
Okay, thank you very much, Laurent, to introduce my talk. And thank you, Juan, also, because your speech introduced well what I will say in this one also. So as said Laurent, we will talk about synchronization and why it is needed in a low power global area network. So low power global area network is IoT by satellite, LPWAN by satellite. So first, I will talk about the relative low efficacy of LoRa in space and why it is so difficult to do LoRa or LPWAN in space. First, what's lower the LoRa throughput when using satellites? Mainly, it's a link budget, which depends of the satellite altitude, but also the inclination of the satellite, and this is related to the orbit of the satellite. And also to the elevation of the satellite in the sky. When you see the satellite on the sky, it could be directly over your head, or perhaps more on the horizon. So this defines a distance. We call this the slant range, and more the distance is high, less the reception is good. It depends also of the frequencies used, and I will give some figure after. It depends, of course, of the transmission power and the antenna gains and mispointing losses, the receiver sensibility, and we will talk also about the Doppler effect. So this is mainly what reduces the throughput of LoRa network in space, but also, as said Juan, we have to take into account the satellites, the number of satellites in the sky. We can consider just one satellite for a very sparse service, or a number of satellites, a constellation of satellites, but the cost is high, so we have to consider that also. And then finally, the last limitation is due to the access protocol type. And as you know, LoRa is using Aloha, and the performance of Aloha in this condition is not so good. And finally, the duty cycle imposed for this communication. So here are some figures. The satellite orbit can be, these are some figures that we take into account in our simulator, and that in general, the figure we can find in real system. Satellite orbit is mainly between 200 and 1,000 kilometer. We take a middle range distance of 500 kilometer. The elevation we choose to be able to communicate with the satellite at 30 degrees to get the longest time to communicate, because if we just point the satellite when it's upper our head, it will be very, very short in time. So we take a large elevation, we accept a large elevation. This and this defined a long distance, about 951 kilometers of distance between the user equipment and the satellite. The frequency is the LoRa classical frequency at 800 megahertz, and for that, with this frequency and the distance, we have free space loss around 150 dB. classical gain, transmit power give us something around 17 dBm of the jet link, and the receiver sensibility for LoRa is defined by Semtech or some equipment, and classically it's around 141 dBm for a spreading factor 10 with a bandwidth of 125 kilohertz, and less when you choose a better spreading factor. Okay. So, considering all of that, if we make the addition of all of this figure, we can see that if we want to have a merge, it's recommended to have at minimum a spreading factor of 10 to communicate with a satellite in this condition. But when the satellites fly by over us, it has it impacts the Doppler effect because of the speed of the satellite. And as we can see in this figure, it was taken in the paper given in reference. More the elevation is high, more the Doppler is high. So it's better to try to communicate at low elevation to minimize the Doppler effect. And in fact, in this other publication, they show that if you take a very high spreading factor, you will be very impacted by the Doppler effect. And then you will have a lot of synchronization error due to problem of synchronization with spreading factor 12 because of the Doppler. And less is the spreading factor, better is the communication. You can send more symbol without error. So in conclusion, taking into account the Doppler effect, we have to have a spreading factor less than 12, it's recommended. So in conclusion, we have it's need to have a spreading factor between 10 and 12. There is specificity also with communication by satellite. It's the time you see the satellite and you can communicate with the satellite. We call this time the visibility. And as Juan said, the visibility is very short in terms of minutes. We have computed several orbits, and we can show that in our case, the visibility was because of the spot size, the satellite altitude, orbits, and so on. The duration for communication, it's less than 4 minutes when the satellite fly by. And we have to wait the satellite. If we just take one satellite into account, we have to take the next flyby between several hours to up to 16 hours for a maximum communication of 4 minutes. But that's not all. The maximum throughput of Allo, you know, Laurent gave us the definition, and we find the same figure in our simulation. But in this simulation, we take a constellation of 25 satellites. And at the end, considering the LOR, the collision that result between the user equipment, the duty cycle, and so on, we compute that if we to have 95 success of probability to transmit a packet in this system, we can just have no more than 50 devices per 10 million of kilometers square. So it's very few. We can just have with LoRa, classical LoRa, very few devices over into a spot if we want to have a very good success probability. And this can be a problem because you cannot offer a service for just 50 devices. So perhaps these figures are very low because we didn't take into account capture effect and some specific things to LoRa that can help a little bit, but it gives an idea of what is the problem. So, very few devices per spot are allowed to make a possible successful transmission. And what are the solutions we can envisage? To have multiple small spot beams. We do that in satellite communication with GEO satellite classically, but this is too costly for nanosat. It needs big antennas, and this is very costly. We can put more satellites into orbit, but it's very costly also. We can consider LoRa with frequency hopping. This can be a part of the solution. And then we can try to, as Laurent explained, to look about the synchronization. And so I will talk about synchronization in LPGAN. It is a solution at least to double the LoRa throughput, as we said, with floated LoRa, but also it can be the start of the solution to plan the communication between the different UO and reduce drastically the collision. To synchronize the network, we can rely on GNSS. It's classical. If the chipset are equipped with GNSS part, but this costs a lot of energy, about 1 joule to get a GPS point. So we won't consider this solution. The second solution is to use LoRa Class B. It gives a good synchronization and beacon, but also an energy-intensive solution. And then we can consider LoRa Sync, as Laurent said, that provide a good synchronization and beacon and an energy efficiency solution. So I will do the same thing as Juan did, to give some opportunity of research relative to that. If we do not consider GPS, we won't have any position of the user equipment, and then we cannot plan the communication when because we don't know where we are and where the satellite is. So we don't know when the satellite will fly by, and you have always to try to communicate. And even if the satellite is not here, this is not good. And we have to develop new strategies to access the network only when the satellite is here. So this one thing to develop. But how to do positioning without a GPS? Is it possible to do it to set a minimalist positioning system using the resize beacon and considering the SNR and the satellite elevation? I think it's possible to know the satellite position and a very approximate position using that. And it will be very useful to compute the next flyby by the satellite. As said Laurent, the skipping beacon mechanism should be done carefully because we don't have to skip the satellite flyby, and it's just several minutes a day, so we have to be very careful, and we have an optimization problem between listening and skipping beacons. It's also complicated to make synchronization with multiple satellites. You can consider a global synchronization of satellites, and it will be better, of course, but very costly. Or an individual synchronization, it's simpler, but how to do that? Is it efficient? Is there a trade-off to consider? And in conclusion of my speech, I will give just some new advances on LP1 by satellite. First, as said, Juan, we have to consider LoRa frequency hopping. This can be coupled with a good synchronized mechanism. There are also some alternative modulation that arrive. There is the one 10-wave society that provide a new CDMA with ZADOF2. It's the same modulation in 5G for the access in 5G. They call this the golden modulation, and they say they have a very good result. Perhaps we have to look about that. There is also, of course, 3GPP and BIoT, but they're in the standard, they are considering GPS and a complete constellation. And how can we do with less satellite, no GPS? A new technology also, which called MyOT, is based on this ST standard, and which was what's called telegram splitting technology by Fraunhofer. And the principle is to do packet splitting over multiple frequency and use erasing codes, and this increased drastically the number of devices without collision. So it could be very good on satellite system. They have tried to embed this system on a geosatellite, and perhaps it could be a solution for LEO satellite also. So there are a lot of opportunities for future research to do, and a lot of interesting things. And just to keep 1 minute to say that, because Juan is here, and Juan is a big boss of the stereo project where we are implied. And I want to say to him that we are discussing now with our colleague of Grenoble to embed a LoRa transmitter with frequency hopping on the satellite for 2024, because we will send a satellite, and we will have a very few space, 5 centimeter square in our satellite, and we will try to embed for the project a chipset. So that's all for my speech.
Thank you very much, Pascal. Now, please remember, if you have any question, write them down. You can also post them on Zoom, but this will be at the end. Now, I would like to introduce you to our next speaker. If we change this. Just give me a second to start the presentation. No, well, no. Just, I ask everyone, including those who are watching, that please give us a minute. We have a bit of a delay with the last presentation, because I have to download the document here, and we had troubles last time.
Puedo compartir.
Now, I would like to present to our last speakers, Marcos Diaz. He's an assistant professor at the Electrical Engineering Department at the Universidad de Chile, and he's in charge of the Space and Planetary Exploration Laboratory. Today, he'll be presenting his talk titled CubeSat Projects in Chile, Lessons Learned and Requirements for Future Missions. So please, Marco.
Thank you. Take the mask off. All right, to be heard. I don't know if the people in the Zoom is hearing or because my microphone is.
Yes, I should be.
It's okay. Oh, it's there. Okay. Just like that. Going to test this. Okay, thank you very much for the invitation and for the time to listen this talk. I'm going to talk about the what we have been doing here in the laboratory, about the CubeSat projects that we are developing and all the areas that we are working. Some of them are related to LoRa communications, others are related to other topics. So, but I'm going to try to summarize all this stuff. But in all of them, we require communication. We need to, whatever we do in space, and this is the main message that I want to transmit to all the people that we have here, is that we want to download. We want the data. We want to measure in space, but we want the data. And for that, we require communication. Okay, why we are doing this? What is the strategy that we are trying to follow with the project? It's because we have certain advantages in Chile. We have a good location. We are a long country. We cover multiple latitudes in the southern hemisphere. So we have a lot of advantages on ground for communication. We are in the southern hemisphere where there is not much ground in solid ground. So we have much more water in the southern hemisphere. We have, because of the geography of Chile, we have different geophysics places. So we can calibrate satellites. We can use different advantages of the climate and the position in Chile. We have the astronomy. That is key as well for us. We have a lot of infrastructure in the north of Chile in particular, but in other places as well. And that is related to the space, the big antennas that usually are underused after a while. So when they are good for astronomy, we use it a lot, but then they are less used because the new big telescope and the big antenna is coming, and we need to find things to do with the antennas that are not used for science or the frontier in science anymore. So we use optical systems as well for space situational awareness, which is a key problem right now for astronomy and for space as well, because we have mega constellations. So 5-7 years ago, there was not this idea of thousands of satellites in space. In 2013, the largest constellation was Iridium with 64 satellites. Right now, in 2022, Starlink has over 2,000 satellites in operation right now. So it's a different scenario, especially in low orbit. And we have the trend of nanosatellites, CubeSats, where we can put miniaturized technology that we develop for astronomy in space technology. It's advancing slowly. Okay, so
what we are doing first in our project is to try to understand what we can do with the satellites in terms of science. This is key for Chile, at least, because most of the resources are coming from scientific objectives, scientific goals. So we are trying to understand the space environment because it's key for what we want to do. We need to understand in what environment we are developing the projects and what could be the effects in certain technology that we want to use in space. So the first missions are, and the current missions as well, are measuring the space environment, the relationship between the sun and the earth, and all the geophysics related to that. The earth has a magnetic field. The magnetic field, it's a kind of shield, a protection against the particles. And the particles, because of the topology of the magnetic fields, they tend to be oscillating between poles and poles, and those are the radiation belts. And we feel particles there, and these particles perturbate the ionosphere, which is a part of the atmosphere higher that is ionized as well. So they are charged particles as well. And those tends to move, and because it's a kind of metal, movement of charged particles produce waves, electromagnetic waves that perturbate communication, GNSS or GPS systems, etc. So we have a lot of dynamics there that could be critical for that, but also we have a lot of particles that could damage the technology that we put in the satellites. And that is what this video represents, is most of the phenomena that we are feeling there. We see the particles, and these particles charge the satellites or produce electronics effects or defects in the satellites. And all this is coming from the sun. So we need to understand what is going on there and what is the dynamics. It's similarly to what we say for a storm here on ground. So if it's going to rain, where it's going to rain and what we need to do. It's going to rain in Santiago, in Rancagua, or in all places at once. So in order to see what we need to do in the satellites, most of the satellites turn off in these scenarios. Yeah, the light is not helping. Thank you. So there are also problems that are related to this and in connection with the search of planets and all the stuff, as well with magnetic fields. So we usually tend to, we know a lot of things now, especially seeing Jupiter and one of its moon. And what happens is if you have a moon, it doesn't have atmosphere, this moon, but it has a volcano. So some materials from the core of this planet, this moon, goes up, but because of the UV radiation is ionized, similarly to the atmosphere of Earth. But these particles, because the moon is moving around the electromagnetic field, the particles move as well between poles and poles in Jupiter. What does produce? It's produce an electromagnetic beacon. So we can see that the planet or an object has a magnetic field because we can see these beacons. And if we can combine these or we can extrapolate this to a star. So we have a planet that has an atmosphere or has a magnetic field, certain things, we can see these beacons coming from the stars. So we are doing this from ground, but it's much easier to do it from space. Why? Because we can see this Jupiter and certain stars on ground because the electromagnetic waves are higher than the 30 megahertz, which is the block frequency of the ionosphere. As I said, the ionosphere is a charged gas that acts as a metal below certain frequencies. So below certain frequencies, these waves are reflected as a metal back to the space. So we need to be in space to detect certain things. And if we combine this with other activities like the transit of planets, so if we look in a star and what happens is that we see a planet, a reduction in the light that we see in a star. So it requires a lot of precise pointing. We need to see a very tiny point. We need to measure what is the intensity of that light and estimate a reduction in the time in this intensity. And because of the wide and the intensity, we can estimate how far from the star is the planet, but also we can combine this with the beacons. So if we are seeing the optical things, but also with the radio beacons, we can see if there is a planet there, but also if it has a magnetic field or certain atmosphere or materials that could be ionized. So all those things requires a lot of things, pointing, but also requires information. We need to download that information that we collect there. Okay, so in that sense, we are also working and paying attention to optical communication. In Chile, we have advantages for that. We have telescopes, as I mentioned, astronomy there. The desert is a good place for doing this. And also it can be complex for this ground-based astronomy. It will be polluting the ground astronomy. So we need to try to be thinking this in advance in order to avoid that just like a Starlink start passing, and we cannot, we do nothing about what is going on with this. But it could be really critical to get in these things. And I'm going to arrive to other communications like microwaves and eventually LoRa, and why those things could be key for us. So how we started with the program, and it was the Suchai 1. So it was a seed program developed by the Faculty of Physical and Mathematical Sciences here at the University of Chile. We developed a Lightning probe. I don't know if I can move here to see all of this. This a sphere that you see in the image is in a sphere that it was inside of the satellite, and it was deployed once in space. And there is a tiny particle counter that it was in the electronics here. It's this circle in one board. So we were measuring the ionosphere and also the particles that were coming on from the solar wind coming from the sun. And so we have some pictures there that was a proof that the sphere deployed, the antennas deployed, we had communication, and we were able to measure the particle counters in different scenarios. This is a kind of a live picture. This is just one point in different points. What we say July here is because all this image here is, it's 1 month. One different time or series of time are different points and different orbits. So we need 1 month to see the Southern Atlantic anomaly, which is the weakest point in the magnetic field where the particles can go lower in this magnetic shield, the magnetosphere. So we need eventually, if we want to study the dynamic of this, we need more points. And that was the next step, to have more points in this. But having more satellites produce opportunities and also problems. It's operational problems, so we need to work in different things. But also we have communication problems, and some of them are because we want to measure with different points. Sometimes we say, okay, how we are going to communicate between the satellites and how we can do this. And also thinking on ground is we can use radio communication between the satellites and eventually with tiny satellites that we are developing femtos, and maybe we can use other type of communication like LoRa for also controlling different sensors in space. I'm going to elaborate later more about this. But also we can combine with instruments on ground that also are related to IoT or LoRa, which is the main topic here. LoRa is very similar in frequency, not the same, but it's similar to GNSS receivers. So, and what we see here is that the GNSS receivers in geostorms, the central image here is in a storm, the same storm that we capture with Suchai 1, and we see perturbation of the total electron content. So the total electron content appears higher. It's not that we have more electrons, but because of the variation of the particles, if we have electrons and ions, a gas, and we inject an electron, the electrons tend to move away and the ions tend to get closer, and that produces a wave. And that tends to produce instabilities in the GNSS receivers and eventually in the link, in the communication that could also be similar in IoT. How important and relevant is this? We don't know yet, but we need to quantify, especially if we want to use this technology in Chile or in the South American region, because this is happening in South America because of the South Atlantic anomaly. Yeah, the new missions were, as I mentioned, following this idea of measuring the space environment with more points. So we started to develop 3 CubeSats, larger, 3 liters more or less in volume, these satellites. But because we are measuring the space environment with magnetometers, particle counters, Lightning probes, different approach to the Lightning probe, but we started to develop other technology that we were not able before with Suchai 1, attitude control. So we wanted to estimate the position. We had the tiny camera and the sphere, and we were able to more or less estimate our orientation, but we were not able to act, to move in space. But right now we have technology, our technology, so we are testing it and evaluating this to move the satellite, but also because we are measuring and evaluating the space environment, we are putting certain technology that we want to evaluate in space in these conditions. And some of these systems are biological, okay? So we have a plant and microorganisms. We started with the plant, but because of the pandemic, we had to move a little the project and we evolved to the extremophytes. The plant, anyway, is in the satellite, but it's very unlikely that survive the launch. We have a graphene, move this. Sorry for that. So, and Suchai 2, we are trying to evaluate a camera, high resolution camera. We are going to test it with trying to measuring light pollution on ground with this camera, but the main goal is to try to evaluate technology that could be useful for optical satellites, for optical telescopes in space, especially thinking in this idea of the transit. But in Suchai 3, we are evaluating the LoRa technology. We have a LoRa gateway receiver in the satellite. It cannot transmit to ground, so it only can receive, but that is the plan. We are trying to evaluate. In potential future missions, we can do it oppositely. So have the gateway on ground and just send signals on ground, or using another satellite to connect with this gateway in space. So we can work with that. We have shown already, and later I'm going to give more details about that, but I'm going to show in what state we are there. Those are the satellites in the final stage before going to US for the launch. And so what we are trying to learn, as I mentioned, we are trying to learn how to deal with constellations. We are working in the idea of the software that could allow us to produce, develop a series of satellites in an agile manner, and how to test them while we are developing the satellite on the fly. And this is really important for us because we are not working with very experienced people. It's people that is learning. I'm learning these things, but also the students are learning. So we need to try to be agile in catching the problems and the errors in the software, but we do not have much time in the end of the mission to run a lot of tests. We need to run the test on the fly, on the way. So there is a lot of work on that. And we are working in the development of the system for acting in space, for estimating and Star Tracker, but also we are working in our own reaction wheels that we are working with DVD motors that we need to adapt a little for working in vacuum and in space. So we have all the system, and we are evaluating different structure. I don't know if you've seen the video. The structure looks like Goldie. It's aluminum ionized, but in the picture it's black. It's because it's wind farm. It's a carbon fiber kind of composite, and that we use. So it's 3D printed. So we are exploring different materials for this. We have also a microwave system that also, as they mentioned, we are trying to deploy a tiny sensor in space and try to locate this with these antennas. These antennas also has this position in order to allow the camera, because we want to calibrate this camera, so we can point it with the beacon, this position of the antennas, these 4 antennas here, this array of antenna allows to say in what direction a potential signal is coming. It's what you see here in the video of the car, which is a toy that we did with just 2 antennas. So we are radiating a signal, and the car is following that signal, okay? So we can do similar things from space with the satellite to point for a calibration in the light pollution, but also for optical communication to facilitate to find the telescope because it's a difficult task. But also we use it for geolocate the femtosatellites in space that could be also useful for locate transmitter of IoT or LoRa transmitter receivers or systems. And I don't know if this ran already, but we are working with the SECHEN in a plasma propulsion system that is working. As you see, it's really tiny. This circle is less than a coin, a 100 pesos coin. But anyway, the main problem is the capacitor is still too big and the power. So we need to keep miniaturizing this in order to make it fit in a CubeSat. So here I'm going to go fast. This is the Plansat mission, the Plansat satellite. We have containers there. You are going to see we have a lot of tests. The main goal is to test the technology, the chambers, basically. So as you see, there are multiple difficulties in measuring this kind of stuff in the system. Stop this. The yellow balloon is really slowly growing, which means we have leakage. So this is advanced, and it's a lot of hours there because it was working more or less okay. The other one, the orange, is not leaking anymore. This is before putting sensors inside. And why we are developing these balloon things? Because we have tiny containers that have been proven in the ISS with the atoms in an experiment, and now in experiments with extremophiles. So we are evaluating this technology, but these chambers are critical for other things. For example, if you have technology that requires pressure or maintain temperature or doing things in space, receivers and things, we can use also these containers to keep them in a much better environment. In particular, for example, the reaction wheels, we are thinking eventually to simplify the problems that we have with them, put it in the container as well. And the microwaves, and this is the board. As you see there, we are also testing a lot the board that we use in some of the payloads. It's Raspberry Pi Zero, the regular one and the 2. So we are testing also, and we have experiments there. They are running, for example, the star tracker. It's being evaluated to take pictures of the stars and run, but also has a catalog of stars that we took from ground, and they are going to be evaluated in space in order to see if they perform similarly here and how much power they consume and how much time takes, how the temperature increases. This is the way that we evaluate the sensor with the extremophiles. We use light to pass through the sensors and detect that light in some wavelengths in order to see if microorganisms are growing in the chamber. But because of the change in colors, we can also see in pictures, in images as well, if we take images, how the colors in the containers are changing. Similarly, in the pools, when the pool gets green in some places, and you have microorganisms living there. So this is the optical communication system. That is the camera that we use, connected to a Raspberry Pi Zero. This is the Suchai 2, and there's Diego, the one that was developing that and integrating this, developing this system and integrating everything to the satellite. So here we start to arrive to probably the satellite that you are interested in, is a Suchai 3. Of course, it's measuring, and it's measuring the space environment. It's having all this instrumentation for locate itself and also orientate itself. It has femtosatellites, small satellites that are going to be deployed here in space, not now or not soon, because it's a little dangerous deploy things in space. But as you see, we have a system, and we use in order to using radio communication between the femtosatellites and the mothership, which is the CubeSat. We can geolocate with certain level of precision the position of the femtosatellite, at least for a couple of days, because we want to use this to study the evolution of the solar storm, a geophysical storm. And this is the way that we deploy the femtosatellites, or we are going to deploy the satellites once in space. But that is going to put it to rotate in space. So we have developed, because of these, certain skills in space, integration, testing, deploying things. If we want to deploy antennas, and evaluation and testing, this is part of the evaluation and testing in US during, I don't know, right. Okay, so also testing for the launch. This is the vibrational test that we performed before the launch, and also the thermal vacuum, or really for the launch, you need to do the cooking testing, which is increasing the temperature, because you are in a very hostile environment in the rocket. We are in a part that is near to the nozzle of the third stage of the rocket, so it gets hot. But we have all the systems to evaluate the environment more or less in space, from minus 30 Celsius degrees to 70 Celsius degrees, and all the satellites and the components were tested in this equipment that we have in the lab. Here you can see we were deployed in a container that is it is a Falcon 9, but the container is the Ion from the orbit, the company, the Orbit. So this is a satellite that has containers for the small satellites. Then they deployed later on, and a couple of weeks after that launch, the Orbit deployed. This is one image of the PlanSat being deployed from the Ion system, and we operate the satellites. We can control the satellites, program the satellite, and download the data from here, from the Faculty of Physical and Mathematical Sciences. It's in the roof of the Electrical Engineering Department. Here we are starting. This is 1 milliampere. There is a 1 milliampere consumption in this payload, but now this payload passes to 281, so 84 milliamperes. So we were able to turn on. That is just one example of what we do. The current results that we do, interesting data that we have been collecting, is the extremophiles. We have been taking pictures and the evolution of the system. This is the system that we took in the satellite. This is the system that is here on ground. It's the counter sample. So we are studying the evolution in both things. And for the July 20th, this is the stage in the counter sample here in ground. It was completely white when we started, so nothing was there. And here it was similarly in the satellite samples. And this is here's in Spanish, but this is a ground. before going to launch, and this is in a space. Here you need to have a lot of imagination to see what I see, but this yellow card here is really important because it's a rad tag. It's a board that we use to see the radiation levels in radioactive places and systems. So it's yellow when there is no radiation, and it tends to be gray when the radiation is high. So the main changes, for example, occurs in this chamber. The other colors are very soft, so it's very unlikely that we are going to catch that in the naked eye. So we need to do certain level of images or use the other instrument to see but the dark, the pyrococcus is very notorious, and we see it. If you have a lot of imagination here in the image, there is no black thing here in the beginning, and start to appear a black thing in this chamber. And as well, we see that we have been getting radiation in the system, and eventually in a video you can try to see this, but in the data it's more or less relevant. We have a shadow here that start to appear that is consistent with what thing. Why it's positioned in some places is because the satellite is rotating, so we are giving certain gravity to the system, and that is what we are showing here. We are taking pictures with different cameras in the satellites. This is our data from Suchai 2 and Suchai 3, and we are taking images of the stars, but also we have a FLIR camera and infrared camera that allows to see if we are seeing the Earth with this camera. But we have images of the Earth. We have a simple model where we can emulate what portion of the Earth we could be seeing in different places in our trajectory. And with that, we have a program to extract that limit from that image. But as you can see, the images are more complex. Here we see the Earth, but the sun is there as well. But we are not able right now to get that information from the image. Similarly, here it's more complex, the image. And here as well, we can see certain things about the white thing. Here is the sun, it's not completely black. So we can extract more information about the other objects in space, and we are working to provide this intelligence to try to orientate the satellite in an automatic way. So and that is what we are. We are just starting with this data. This is a kind of gift of how the satellite are seen. So we are rotating. Other data is reflecting this. But what this is what we are seeing. And there is certain level, they are more or less fast. This is with samples with 2 seconds, and they are slower, 5 seconds apart. So we can see that we are rotating and moving, and we are trying to find with certain level of intelligence what we should be seeing in this sequence if we combine with other data. Here is the images about the LoRa receiver in the satellite. So we also collaborate with the other colleagues in the development of the antenna. This is a 3D printed antenna in ceramic thing, Francisco Pizarro and Eva Rayo from Spain and Chile, respectively. And also Sandra Céspedes in collaboration, and right now we hopefully with other guys here with the IoT. So far, we have confirmed that the receiver is working well, but in the satellite, okay? So we haven't received any package yet from ground, and this is because the satellite is rotating too fast for the system. So we need to stabilize first the satellite in order to try to start to probably getting a connection if nothing is broken, if the cable doesn't unplug or we are having any trouble. So we have different, you are not seeing the video, or it's not appearing there, but in Zoom it's appearing. Who has Zoom? No?
No, that's actually a Zoom screen.
That is the Zoom screen.
Yeah.
Okay, so there are some videos that are running in my computer, but I'm not seeing them in that screen. I lost the communications.
Oh.
This is what.
Yeah.
I'm gonna try to go back. Okay, that is the video. This is how this receiver has multiple receivers, gateways, to compensate the Doppler. So this is what we use. We do try to keep it simple. We have multiple receivers, different frequencies, and this is the satellite where we are calibrating for multiple things previous to launch. But that is more or less the system. The antenna is below in the satellite. That is the part where, and this is the phase array that we use for the femto satellites. And here's the antenna and how it's located in the satellite. So there are a lot of issues with this. We need to try to avoid the system. We get a lot of trash in the system anyway, and for this reason we know what we have. But we are sending messages. This is the transceiver here in the transmitter on ground. It's very slow. What we are transmitting there in this example is zero numbers and a spell, and we are receiving there, but we need to catch it from a lot of data. So this is for this reason we know that we have, because it's operational, because we get all that information in the system and we can read that data, but we are not receiving this small package of the packets yet from ground. So this is a project that requires a lot of people here. It's not nothing that I'm not doing this alone. It's a lot of researcher peoples, students, and also researchers from other places, and that is the goal. So the main goal is that we try to use all these satellites and problems to do this with more people. That's it. Sorry for the long time. Thank you.
Thank you. So I would like to thank Marcos for his talk. Now I would like to invite you to the question section. Let me change this over here. And so I can see questions online. Okay. Okay, so since the questions were left to the end, I would like to order these questions by speaker. So please, if you have any questions for Juan, if this can be also through Zoom, I can see those questions too. So if anyone has a question, please tell me. I will repeat the question and invite Juan over when question starts. So does anyone on Zoom or does anyone have any question? Because if not, I do have one that I wrote down because I would have forgotten by now. So okay, I wanted to ask you, or maybe by yours, so you can appear. Yeah. I want to ask you at the very end of your presentation.
Yeah.
You talked about that you've been working with students and other researchers and this downlink and uplink problem. And I wanted to know a bit more about the research that you, your team have been developing. Maybe anything that's interesting that you would like to share?
Right. So, for instance, we've been working with Sandra and Guido, some student from Argentina who is connected also here, and also some colleagues from Ireland on the uplink transmission policies, which is one of the topics I mentioned. And we have a paper that was recently accepted on IEEE Access. And what we tried to work on that research was to approach the question of when is the optimum time for a given IoT device to transmit an uplink data. And answering that question is not so easy because you need to account for not only the orbital dynamics, that namely when the satellite is going to appear, when the satellite is closest to you, because the trivial answer for that question would be, well, in fact, the best moment to transmit the packet is when the satellite is right up on the sky, and not when the satellite is on the horizon because it is farther away, and of course not when the satellite is on the other side of the planet. So that's that's the trivial answer. But the issue is that another thing that you need to take into account is that if a bunch of devices are all together and they have the same decision to transmit when the satellite is right up on your head, then collision will happen. So also there is a trade-off there. So it's not only a matter of having the satellite on the closest distance possible, but also having some awareness of which is the traffic condition where that device is located on. So in those cases, it might be much better and much smarter to, in some times, to also transmit in a elevation near to the horizon, so that you can offload the moment where the satellite is on top, so that other nodes can also transmit. And in that paper, we basically studied some approaches to force that decision and to spread the distribution of the transmission in such a way that the collisions can be reduced and therefore, yes, optimize the throughput of the system.
Okay, thank you.
Yeah.
Yeah. Does anyone else have a question? I don't see any questions also here. Questions?
Yeah.
Please tell me, I will repeat it.
So you mentioned that the optimum instance to transmit should be at 90 degrees, right?
If you want to optimize like the spreading factor, for instance, you want to use the strongest modulation. Yes, that's
safe to generate some offloading. You could use some other angles.
Yes, exactly.
For those cases, in the paper you wrote, how did you consider the communication channel?
We're using the free space model for this case because we are not really modeling really detailed radio frequency aspects. We are just modeling the medium access control. So we are assuming just free space model, very simple. No shadowing and no multipath. So yes, so adding more complex channel model is one of the open topics I highlighted in my last slide. So yes, the idea is to combine that in the future. Yeah.
So any more questions? No? Okay. So next, I'm gonna change. Oh, there is a question here. There. So now comes the questions for Pascal and Lauren. And we have already a question here from Sandra. And she's asked do you plan to implement the proposed LoRa sync in their testbed?
Okay, so I guess I can answer that. It has been implemented, in fact, and so that's what I showed with the proof of concept in the end. However, I have not provided a performance evaluation with the implementation of LoRa sync because in this contribution, I did not talk about the capture effect yet. And we discovered later, in fact, while doing the work, we discovered that the capture effect greatly impacted the throughput model. And so in order to compare the performances of the testbed with models, we had to come up with new models that took capture effect into account. So that's why it was done in a separate paper as the synchronization one. But in fact, yes, it has been implemented and it works.
Okay, thank you.
You're welcome.
So Anyone else have any question for Pascal or Lauren? No one?
I can shoot one to Pascal maybe. So you mentioned this MyOT modulation in your last slide, or standard, I would say. Actually, do you have any idea how it compares with long range frequency hopping spectrum? So which is the similarities and which are the difference with the lower one proposal?
Not at all. We just have a presentation of MyOT in the lab, and we don't have any time to compare this, but we will do. Yes, it's okay. It's a little bit different because in frequency hopping spectrum you are using multiple frequency. But you do not do error correction, and with MIOT you split the packet over different frequencies, and then if you receive at least 50% of the packet, you can rebuild it. So perhaps this is the difference as a use of erasing codes. Okay, I don't think that in FHSS there is erasing codes, but we will look carefully about that.
Okay, thank you. Does anyone else have a question for Pascal and Berto? For Pascal and Lauren, sorry. Says Pascal Berto. No one? Okay, so now we'll proceed to the questions for Marcos Diaz. So, does anyone? Yes, we have one. We have a question from Sandra. I also have a question. So, please, you could come here, and I will check on the camera. So, Sandra's question. So, what was the camera? There. So, Sandra's question is, will there be a launching of a new satellite anytime soon? And will it include an IoT model?
Yeah, the answer is I'm trying to survive to the launch of this week. But yeah, crazy it sounds. Yes, the idea is to have new missions and dedicated ones. So because what is going on is that we are developing these satellites with certain scientific goals. And because we miniaturize certain instruments and reduce, we make volume for other tests. In this case, the IoT, the LoRa receiver was more or less that idea. So the satellite is not optimized completely for that payload. So eventually, considering this as a dedicated mission, we can start to include more receivers or transmitters as well, as you mentioned. So maybe we can test both channels or both directions. And the answer is yes, we are trying to apply for these things. We haven't been successful yet. They think that this is too risky, this kind of stuff. Maybe they are not understanding what is this about and whether their potentialities are. But the goal is to try to find a mission for this soon.
Okay, thank you. Now, does anyone else have a question for Marcos?
I can put one to Marcos.
Thank you.
So the Raspberry Pi you mentioned,
yeah.
Is there any studies or ideas on what is the expected lifetime of the Raspberry Pi in space? And secondly, do you consider some shielding or some preparations to send it to space?
Yeah, those are really terrific questions. We know that Sorry uses Raspberry Pi Zero, but because those things are companies or things, is they don't tell you what they do and how long it's working in a space. So what we are trying to do is exactly that, trying to give information to the community how well they are working. In fact, we have 9 Raspberry Pi Zero in space, so we can provide certain statistic about them. And also, and we have contact right now with 6 of them. So Chai2, it's given us some issues with the UHF receivers, but we need to solve, and that is Marco's problem or Marco's future problem. But it's there. We have contact with him, and it's with it, and it's safe. But we have certain statistic about the Raspberry Pi Zero. Right now, what we are doing with the Raspberry Pi Zero mainly is just being careful with it in the satellite where you put it and the way that we use it. And one that is it's usually taking too hot. What we do is connect some metal to remove the heat from it. We need to describe eventually in an article about or whatever we do for communicating that information to the community, what we do. But there are things really simple. We are not doing nothing very special. Right now, the data that we are collecting, the environment is not that bad in space and temperature and radiation. So it looks like it's okay. But how long it's going to last? We'll see. Yeah, we'll see. And that is the information that we want to provide to the rest of the community. It's a really good question because it's really powerful. It's providing us a lot of power in space for computing, for doing things, and also for reprogramming the system, because we can run Python. So we can just send a new Python, new PI, and we can run a new project, a new program for the payload or for the experiments or whatever we are trying to do.
Thank you. Well, I have my question, which is about the Landsat part, about the external. I was really interested in that because, I don't know, it looks fun. I just can say that I really like it. And I wanted to know a bit more about it. For example, what specific measures have you measured using this extremophile? What more of a specific application that you've used during your test?
Yeah, for us, because my background is more about the instruments, the idea is to try to develop the container and the instrument to test the system in a space and how to try to validate that with images. So we are using similar techniques that we use for astronomy, like photometry from images, to estimate if something is growing. But basically we have a light source that crosses the chamber and detectors in the other side. And when this one it's reducing, the detector is reducing the amount of light that is receiving, you can say something is in between. And something that is in between is probably alive, an extremophile. It's similar to what you see in a pool that gets green. So when it's clean, you see the bottom of the pool, but when it's not, when it's green, you don't see the bottom. So the receiver is getting less light. So with that system, we get more sensitive than with the image. But we use the image to compare really, because the problem in space is if the detector gets degraded and reads less, we can say, okay, something is growing there. But with the image, we confirm that is that. The other part of the question, if I understood well, is why this is important. The extremophiles could be used. They are microorganisms that resist to very hostile environments. And we think that those things could be useful for multiple things in space, especially if we have humans in space. Those extremophiles could clean water because they eat very toxic things and live in very hostile environments. Some of them are used to produce, for example, the pyrococcus that is growing produce hydrogen. So we can produce in a very natural way the hydrogen, so power, the energy in space, and produce oxygens as well. So we can produce oxygen in a natural way, and they can eat minerals and these kinds of. So eventually, in a mining exploitation system in a space, they could be used. And also in the other in another branch of this is the science. I cannot say that right now. So it's the search for life. So we need to try to understand what life could survive to the space environment in order to search for this, and what are the signatures of this, because we are searching for both things, for things that died already and things that are alive, and in what condition, under what environmental conditions. So those is more or less what we are exploring with that. But for us, because we are the technician of this, the containers, the instruments, the detectors, the images for estimating this is the key part. I'm not a specialist in extremophiles, which is the cool part, really.
Thank you very much. Yes, that was very much what I wanted to know. So thank you.
No, thank you very much.
So I would like that we all thank again our speakers. And now I want to invite you to have coffee outside. So for everyone who's watching this online, this is the end of the webinar. Hope you have your own cup of coffee already out there, so you can join us in your hearts. So thank you very much. Thank you for the report. And now let's have it.
So before closing, I want to thank a lot Sandra, that she put together all this workshop. Amazing job. Thank you, Sandra, for that. Thank you, Claudia and Cesar. They managed also all the logistics here yesterday. It was amazing. Thank you for arranging the room. Marcos Diaz gave us a fantastic visit at the SPED laboratory yesterday. We had a chance to really see the real operations of the QSAT. That was also amazing. So thank you, Marcos. And thank you also, Ivana, for arranging all the hosting us today in the workshop. So I wanted to mention that, acknowledge the right people here. So thank you. Thank you, everyone.
Yeah.
Thank you.
Thank you. Bye.
Bye.
Thank you.
Ivana, you're gonna be doctor next week, right?